Hello, everybody. Today, we'll continue our models and we'll talk about MG1, MG infinity, MMskR models. MG1, as candle notation, M stand for Poisson arrival lambda, G general service mu, okay, with variance sigma square, with variance, given variance, unknown distribution. Here in G general, it's a general distribution, unknown distribution. So we don't have an equation on it. So because of that, we add the variance. The variance means the difference between or around the mean value, mu, plus or minus sigma square. So that's why we will include in our formula sigma square variance. One server, infinite size, infinite population, FIFO. So the MOP of MG1 will be like before, lambda rho lambda over mu less than 1, P0 utilization always equal 1 minus rho, L equal rho plus rho square 1 plus sigma square. This is variance here. Here we have variance, mu square over 2, 1 minus rho, and the other relations. So this is the general formula of L in MG1. Special case, when we have MM1, okay, MM1, the M exponential distribution of service time, it's special case of G, general distribution. So M exponential distribution is it's special case of MG1 with variance 1 over mu square. Replace sigma square 1 over mu square in this equation to get our old equation L equal rho over 1 minus rho. So M1 is a special case of MG1. Okay, this is the equation of L, and the other relations are known. Okay, any question for MG1? It's fast definitions. Okay. Okay. Now MG infinity. The same, M Poisson arrivals, G general service mu with variance, unknown distribution. Now infinite server. Okay, infinite server, infinite buffer, infinite population, FIFO. This is MG infinity. To get MOP, this. In infinity server, we don't have a Q. No LQ. LQ equals 0, WQ equals 0. And L equal rho equal lambda over mu. Okay, like MM infinity. It's similar to MM infinity. L equal rho over mu, W equal 1 over mu, WQ 0, LQ equal 0. These parameters, MOP's parameters matrix, similar to MM infinity. The exception here, MG infinity, P0 equal E power minus rho, and Pn equal E minus rho n over n square. Okay, for n. This is the difference between MM infinity and MG infinity. The other parameters, W, WQ, L, LQ are the same. For MM infinity and MG infinity. Okay? This is fast definition. It's general distribution. We don't have a lot of example on it because it's general distribution. Okay. Now we'll talk about MMskR. Before we talk about MMsk, finite buffer. Now we have finite population R. Finite population R. As candle notation, the same, MMsk is the same here. Poisson arrival, exponential service, S server, independent servers, parallel service channel, identical servers, random choice of all idle are the same. Even here, finite size, finite system size, total n will be maximum k. It's a buffer. So till now are the same as MMskR, like before. Now the updating now R is finite population. Our customers can be served. Only our customers can be served. So it's special case here. Our customers can be served. Finite population, okay? And FIFO. So if K less than R, if K less than R will continue. Else, if K bigger than R, the limitation will be in R numbers of customers, not K. Okay? K, size of the buffer. How many customers or system inside the buffer in the queue system? R, the number of customers can be served only. Okay? So, finite population R, special case on arrival process, R independent source, all sources are identical, arrival rate lambda for each source. This is special case here. For each source, no arrivals if all R sources are served. Okay? No new customers. If R are served, the system will finish. The system will be finished. Okay? This system will serve only our customers and finished. Okay? For today, for months, whatever. Per unit. Will serve our customers per day or per month and finished. So this is special case. So in steady state distribution, finite population R, system is in state N if there are N customers in the system, waiting or services. Here we assume K less than R. Here in this slides, we assume K is less than R. If system in state N implies R minus N are expected to arrive. We have here from 0 to R, maximum R customers. Okay? It's different than buffer. If system in state R means 0 customers are expected to arrive. Let P n probability that N customers in system. Okay, so given example, this is example. Given facility with 6 identical machines. If we have example here, factory or any workshop or anything with 6 identical machines. Failures on any machine occur at rate lambda. Okay. If machine failed, is taken to the maintenance. Each machine needs 1 worker for maintenance. 1 worker. As here. Maintenance workshop has 3 identical workers. S equal 3. We have 3 workers. S equal 3. R equal 6. Here, 6 identical machines. R equal 6. We have here S equal 3. Each worker works at rate mu. So we have 6 machine, operating machine 6. Each one arrival rate lambda, each one. Our system is inside this workshop, not outside, not outside. This is our customers. These 6 machines, our customers, will enter the workshop for maintenance. So our workshop is our system model. So at n equals 0 inside it, P0. Here we have P0. So expected arrival rate will be 6 rho, 6 lambda, 6 lambda. Okay. If any machine has failure, will go into the workshop. So will be n equal 1 inside the workshop, n equal 1, and arrival rate will be 5 lambda. Another machine, if failed, so n equal 2, arrival rate will be 4 lambda. Assume another machines has failure, go inside the workshop. So n equal 3 inside workshop, our model here, arrival rate will be 3 lambda. And so on. N equal 4, n equal 5, n equal 6, arrival rate will be 0. No customers will be entered. Okay, 0. This model is finished. So the state of the system is n from 0 to 6 only. Okay, so that's why the rate diagram is arrival rate if state n means 6 minus n lambda for 0 n less than 6. For number of machines r will be r minus n lambda. Okay, n between 0 r. This is arrival rate. The service rate will be finite number of service s equal to 3 in this example. In this example, s equal to 3. So if system is state 0 n 3, so will be n mu. N mu. Bigger than 3 will be 3 mu. Okay, is similar here, similar than MMskR. But for number of service s will be, service rate will be n mu for n between 0 s. Bigger than s to r will be s mu. Okay, so any question here? It's clear?
Yeah, cool.
Okay, so balance equation. Here in this model, Karnoff change model in finite population source model, we have s equal to 3 in this example. First machine, mu, the service time, mu. Second machine, 2 mu. Third machine, 3 mu. Fourth, 5, 6 will constant be 3 mu because s equal to 3. So s equals 3, s mu here, okay? But in the arrival process, we have different than before. For first arrival, the expected arrival rate will be 6 lambda. The second arrival will be -1, 5 lambda, -1, 4 lambda, 3 lambda, 2 lambda, lambda. This is new in this model. All models before are constant lambda. The arrival customers will be at constant lambda. But here, no. The first one will be r lambda, will be r lambda. The second will be r minus 1, r minus n lambda, r minus n lambda. N equal 4 will be r minus n. R here 6, n equal 4, so 2 lambda, and so on. So for balance equation, cut 1, this area, this cut, this region will be 6 lambda P0 equal mu P1. In cut 2, 5 lambda P1 اللي طالع منه السورس اللي طالع منه بوزيتيف طالع منه فيت عليه نيجاتيف اوكي بوزيتيف طالع فيت عليه نيجاتيف اوكي P1 equal 2 mu P2 and so on till last cut will be lambda P5 equal 3 mu P6. Okay, here we have constant 3 mu. So for R machines and S servers, if n between 0s, so the equation, general equation will be r minus n lambda Pn equal n mu Pn plus 1. For n between s and r, the same here, r minus n lambda Pn equal and S mu Pn plus 1 S. Okay? Okay. This is the balance equations to get these values. This is our solution to get these values. 6 lambda P0 equal mu P1. Okay? Implies that P1 equal 6 lambda over mu P0, which is equal 6 rho P0. The second equation, replace P2 function of P1, replace P1 function of P0, we get 30 over 2 rho square P0. And so on, and so on. Replace, okay? We replace each one by one to get P6 equal this number, rho 6 P0. Okay? This is our example. So, also, we want to calculate all the P1 till P6 are functions of P0s. So, we want to calculate it P0. P0 from this equation, summation Pn equal to 1. So, P0 plus P1 plus P2 plus P3 plus P4 plus P5 plus P6 equal to 1. Replace them to get this equation minus 1. Okay, inverse. So P0 equal 0.0837 from this equation. Okay. So the solution of balance equation will be similar exactly like MMskR in addition here. So P0, this equation is for MMskR only. Now we added R population, so will be times R factorial over R minus N factorial inverse. So the same equation of MMskR times R factorial over R minus N factorial. If we go back here, we can conclude that. Okay, P1, it's, I'm sorry. هلا جاي السؤال. Sorry. Now, Pn equal rho n over n factorial P0. Also times R factorial over R minus N factorial for n less than S. For n between S and R, rho n over S factorial S power n minus S P0 times the same factor here, R factorial over R minus N factorial. So these equations, this P0 and Pn here and here, are the same equations for MMskR. In R, we multiplied by this factor, R factorial over R minus N factorial. Okay? Okay? This is how we calculate. Okay, MOP. Effective arrival rate, lambda E equal rho times R minus L or LS. Utilization always will be 1 minus P0. Utilization will be always 1 minus P0 in all models. This is constant equation. Utilization of the system always will be 1 minus P0 in all models. So in MMskR MOP, LS will be the general equation, summation NPN from 0 to R. It is the general equation. LQ, summation of N equal S to R, not 0 to R, from S to R, N minus S PM. So these are general equation. And we have W equal L over lambda and WQ LQ over lambda E. So this is general equations, no specific equation. We don't have specific equation, okay? These are general equation. Just calculate Pn, P0, and so on. Okay, now we'll take our example. Okay. The same example as before. A factory has 6 identical machines for production. Failures occur on each machine at a rate of 2 failures per day. according to Poisson process. The maintenance department has 3 workers, S equal to 3. All have the same experience, same mu, same mu. Once a machine failed, one of the workers is called to repair it. Each machine has 1 worker. If all workers are busy, the machine is put in queue or a waiting list for repair when workers available. So we have queue system. The repair time, mu, is exponential distribution with mean 3 hours. Okay, each machine need 3 hours to be repaired. Assume factory works 9 hours a day or per day. So the questions are, what is the probability that all workers are idle? On average, how many machines repaired in 1 day? Lambda E. On average, how many machines waiting for repair? LQ. What is the probability that all servers are busy? What is the expected time until a failed machine to restart operation? So WSC. Okay, we'll go through the solution. Before we continue, we have lambda equal 2 failures per day, which is mean 0.222 failures per hour. The service time is exponential and each machine needs 3 hours. So mu equal 1 over expected time, 1 over 3. So rho equal lambda over mu equal 0.66 less than 1. It must be less than 1 to continue. So in this example, we have 3 workers inside the workshop. So number of servers will be S equal to 3. We have 6 machines, so the population size is R equal 6. So the number of states here, N equal from 0 to 6 only. Okay. So the model, this model will be MM36. MM36. Okay. Here, we don't mention the K. We don't mention K. So assume here, in this model, assume that R less than K. The limitation will be on R. Assume in this example, because the given don't talk about K buffer, so assume, we'll add this condition, assume that R less than K. So for us, K is infinity now. Because R less than K, we assume K is infinity. Okay? So, okay. Use rate diagram or the given equations. Okay, we get P1, P2, P3, P4, P7. Okay? So P0 before we calculated P0, 0.0837. P1 will be function of P0, 6th row P0. This P1, P2, P3, P4, P5, P6. Use these equations to get sum of all P's. Probability will be 1. It's exactly 1, so it's true, it's correct. Now we want to calculate L. L, S or L equals summation of NPN. L is summation of NPN. So NPN will be 0, NPN 0, 1 times P1, 2 times P2, 3 times P3, plus 4 times P4, plus 5 times P5, plus 6 times P6 to get these numbers, add them to get L. So 2.22 is for LS or L, the average number inside the system, L, okay? So this case, we can calculate it in this table. So Now, the first question will be probability that worker are idle. Worker are idle means probability all machines working. All machine working means n equals 0. All machine working means no machine enters the workshop. No machine enters the workshop means n equals 0, P0. So P0 equals 0.0837. Second question. Average machines repaired in 1 day, lambda E. We have lambda E equal lambda R minus LS. Lambda equal to R6, LS already calculated in the table before, 2.22 equal 7.56 machines per day. So average machine repaired is 7.5 machines per day. Third question, average machine waiting for repair. Waiting for repair is LQ. The same as LS. LQ equals summation from S to R, N minus S, Pn. So, N equals S. Here S equals 3. So N minus 1, 3. 3 minus 3, 0. 0, P3. We ignore it. 0 times P3. We ignore it. N equal 4. So it will be 4 minus S, 1 P4 plus 2 P5 plus 3 P6. From the table, we calculate them to get LQ will be 0.36 machine. Okay? Any question here in this equations? Any question for this slide? Okay, continue. Let's continue. Probability all servers are busy. All servers are busy means if we have 3 machines in the system, or 4 machines in the system, or 5 machines inside the system, or 6 machines inside the system. So we'll add all the probability, P3, P4, P5, P6. Okay? Expected time until a failed machine return to operation, WS equal lambda S over lambda E, which is equal 0.29 hours. Okay? We have less than 1 minute. Any question? This is end of our course. We'll see you on Thursday. Okay? Any question now?
لا تمام.
Good. On Thursday, we'll talk about our finals. Okay? See you on Thursday. Bye.
Bye.